Then okay, then right, coming to elaborate about the semantic computer vision tasks, right. So one of the things that that one does is what is called recognition. This actually comes under high level vision. So it's like saying that, right, given an image where there is predominantly one object, right. If you see these images, I mean, the ImageNet is actually a database which is very, which is very huge, and this was one of the very first data sets, which really helped, right, deep learning approaches to actually emerge. Right, it has about, say, 1000 classes and so on. By classes we mean, right, 1000 different objects for which you have different images taken from different posts, different viewpoints and all of that. And the goal is that, right, can you actually classify each, can you kind of recognize the object, right. And if you notice, right, for example, the first one, it says a mite, right. So there is a small little mite right out there in the image. So if you see here, right, so again, right, there is a mite, and you show the whole image, right, to the network, right, in this case, and it is supposed to tell what object it is. There could be other things in the scene, right. There could be some background and all, but it is supposed to predominantly pick up, it is supposed to pick up the most significant object right out there. So for example, right here it's a a cherry, or what is that, a Dalmatian, yeah, Dalmatian, right. Now and then you have a mushroom here, right, and then you have a leopard there and so on, right? And sometimes, right, it can also go wrong, right? It doesn't mean that, right, I mean, every time you get 100, I mean, every time you will be able to kind of, right, get it right. Sometimes confusions can also happen. In fact, the interesting thing is that there is a whole area called, say, adversarial deep learning, right? How many of you have heard about it? Adversarial, right? So adversarial, where you actually fool a network, right, into actually classifying things wrongly, even though you as a human being will never go wrong. I mean, it's possible, and that's why it's like a slightly a slippery slope, right? I mean, to be what do you say, right? To be swept away by all of what you see, right, is also not really very right. We should apply our head properly to sort of analyze, right, what's going on. It's not true that, right, all that you see is like, what do you say? I mean, you can't just buy all of that, right? You have to also apply your head a little bit, and of course, there are so many people that have done that, and I've shown that, these things can be very slippery. Then object detection, right? This is another thing. So right, between the earlier one and right in this one, you see a difference, right? In the earlier one, I had an image, and all that I had to tell was there an object in the, I mean, right, what object was there in that image, right? But now I'm also putting a sort of a bounding box, right? I'm also localizing, right? I'm also telling, for example, right, what is, for example, right, if it's a static right image, right, then I'm saying that here is a bookshelf, right, here is a stove, and then here is a TV monitor, right, and there is a bounding box around it, right. So I'm able to localize, right, which is a very important attribute. You should be able to localize things, right. And for example, there's a plate here, and it could be object, and many a time, right, faces are very important, like all your, I don't know, social media things, right, where let's say, where whenever you upload a photo, it says, if it is already somebody that that was already in your circle, right, it will say that it's that chap or it's that girl, whatever, right. So face finding, or face recognition, where you also localize, right, put a kind of bounding box. Or it could also be something like this, right, where you have a video playing, right, on the right side. It's called the YOLO, and where, right, you are able to sort of put a bounding box and also give sort of a probability score, right. You see that it's saying some 99% something, right. So it's like 0.99 sort of probability that it's actually a person, and sometimes it could also be a low probability if it is not, if it is a little unsure, and so on, right. But yeah, but then, right, typically it can also give you a confidence score as to how confident it is that a particular object is what it thinks it is. Okay, then yeah, so I think, right, this we already kind of talked about, right. So what again, right, what kind of features to pick up, right, that kind of changes from one approach to another. Even today, right, there is nothing like a universal acceptance of what can be a good facial feature. Nobody knows. Okay, so people have different algorithms. There are these data sets that are already there, and the way this game is played, right, is like this. I mean, if you say that, right, you have your own face recognition algorithm. Earlier days, right, you could just show it on some sort of a data set that you might capture yourself or something, and then say that, right, no, I'm doing quite well and so on. But those days are gone now. So what happens is there is always a curated sort of a data set that is available, and for which, right, you can only take some things for training. There is a protocol. You have to follow that protocol, and whatever algorithm you develop, you need to show on that database what you get. So that's a database that's like universal. not just one, right? There could be multiple, but then, right, those are the ones that let's say people will look at what kind of scores, right, you are able to get on those, and not really on something, right, that you gathered yourself. So your images could be just limited in number, right? Whereas they will have plenty of cases, difficult ones, simple ones, and they'll say, right, on that you show me the score, and then you have challenges and so on. I don't know, you must have seen, right, these conferences that are there, CVPR, ECCV and all, they have these workshop, which could be a challenge. So where each time, right, they will release a data set where only certain things are exposed to you, so you can train your network to beat those numbers, or to emerge as a sort of a top, this one, a contender. But then when you finally upload your code, right, they will have a different data set which is not shown to anybody, and they will run it on that. And then when they declare the winners, right, depends upon how well you did on that, because that, let's say, right, nobody saw, because sometimes people can sort of fudge, right. I mean, if I showed you what it was, so you could fudge, and do something which is improper, right. So that's why they hide the actual thing from you, and the hope is that if you've done well there, you should be able to do somewhat well on the other data set also, but it doesn't automatically work that way. And sometimes, right, you might be surprised that somebody else will just go above you. Then number plate reader, right? This again, right, another sort of an application where you have a semantic information, right? We want to know what is that car and so on. Then segmentation is another very important task. If you see a difference between image recognition to sort of a classification to segmentation, right? In classification, or the image classification part, we had put actually a bounding box, right, which could also have contained a background and so on, right? Because the bounding box does not really, it's not like it's enclosing only the object of interest. There is also other things spilling into the box, right? Now here you have to kind of declare this one. You take a pixel, you have to declare which label it has, right? Every pixel you have to kind of declare a label for it. For example, if you had 5 classes in the image, like you had trees and road and whatever, right, wall, maybe car, maybe people, right, whatever it is, right? Now every pixel has to be assigned a certain class or a class label, right? Which means, right, which is why it's called a segmentation problem, where for example, right, you have to, so in this case, right, you see that the person is right, is kind of given in red, the vehicle is given in a blue color, and the road is in a certain color, right? Yeah. Well, you see, there are algorithms now which are in real time, but this one per se I do not know. Okay, but yeah, but there are algorithms these days which are almost real time, which can run in like 5 to 10 FPS at least. I mean, 30, I'm not sure, but 5 to 10 FPS. Again, right, I mean, there's a trade-off, right, between the accuracy and the speed, always. But the interesting thing is that these are things that we couldn't have done, 10 years ago. I mean, so that way, right, it looks like an easy thing now, right, after somebody has done it. And see, the catch is also here. See, when you show these things, right, there are certain things which you hide. I mean, in the sense that right, there is also a lot of, you see, annotation, right, that's happening, right. Somebody has to give you a ground truth sort of annotation, right. Somebody has to tell that, okay, right, here is the car, right, I have to label all the pixels. Then here is the person, I have to label all the pixels such that I hug the contour close to the person, right. I cannot allow the ground truth to spill over. So somebody has done all that annotation. Then you are sort of showing a network and saying that, hey, look, right, if I push this image inside, that's the output rate which right, you should be able to get, and here is the output rate which I have. The real challenge is if you don't have that kind of information, then all these guys will not work, will be in trouble. Right? This is because they had this annotated data to help them. Okay, a lot of these things are actually because somebody is annotated. Somebody sat down, not just one person. Right? There is a bunch of people, right? I mean, which actually take up these tasks. People are paid to do this, right? In order to what do you call, annotate and all the ground truth. Right, and that's why, of course, these methods work so well. But there are other ways, right, in which you can do what is called self-supervised, right, wherein, let's say, you don't even have that information and you have to sort of self-supervise. It's like saying that I myself have to sort of take a call. See, for example, right, to give you an example of self-supervision, right, it will be something like, suppose I had a camera, right, and suppose I move from, let's say, right, I take an image and I want to see what kind of a depth I have. I cannot, right, because I have just one image, first of all. Now, if I don't have a ground truth depth map, right, to learn, Then another way, right, to kind of look at without a ground truth depth map is to sort of take another image. So I move, right, I take another image, then I sort of see, right, what kind of a depth map if I were to estimate, and if I were to compute my own motion from, let's say, point 1 to point 2, how do I combine the two such that if I, because see, whenever you go from one image to another, right, there are ways to actually go through. Okay, there is what is called a homography. A homography is like, is like a 2D transformation, which is kind of globally applicable on one, which you can globally apply on one image to reach the other. Okay, that is the simplest way in which you can get from one image to another. But if it's a 3D scene, you cannot do. A single homography does not work. Okay, a homography works under certain constraints. Okay, which we will of course talk about when we do, I think, this one, stereo geometry, right? We'll talk about that. But then in general, right, if I have a 3D scene and if I've translated, there is no way I can go from one to the other using a simple global transformation. The only way I can go is I have to get an estimate of what my, say, depth map is, and I have to get an estimate of what is my rotation and kind of say translation in the world coordinate. So it's like a 3D rotation, right? I would have undergone from here to there. I would have undergone a 3D rotation. I would have undergone a 3D translation. That has to be estimated along with a depth map of the scene. Now, if these two things come together in a correct way, then I can go from one image to another. So the loss, right, if you think about it, that self supervision comes from observing two images, and that is the only supervision you have. You don't have a ground truth, right? There is no depth map that somebody will tell you, hey, like, yeah, what you did was correct. The only way you do is what is called self supervision, which is like I ask the network to make an estimate of the depth map. I don't have a ground truth. It actually right, estimates a depth map, estimates the pose. Pose is this R and T, and then applies it to see whether I'm able to go from view 1 to view 2. And this you can continue doing over different images, lots of images, and then you help a network sort of figure. So that's like, it's like self supervised, right? I don't have ground truth data, but many of the things that are shown here are all, right, driven by ground truth, right, which is a lot of work, right? But then the world is going towards self supervised and so on, right, where let's say, you want to do in a more sophisticated manner. You may not get the same level of accuracy, but then people don't mind that, right? I mean, they still like the fact that you've applied certain sensible things, right, in order to do the self supervision. The whole challenge is how well do you actually arrive at that self supervision loss, right? What is a smart thing to do, right? I mean, otherwise you can do plenty of things, but none of them may work finally, right? So the catch is what is that loss that you will actually pick up? What is that cue that you will actually pick up in order to be able to kind of, right, make this one a prediction of the depth map and the pose, right, in the right, and okay, that is there. Then this is of course a segmentation problem, and then there is also, yeah, I think this is just another example. This is a video, and again, right, when you play a video, it could also be that, right, you transfer information from frame to frame and do it, and sometimes people do it on an individual frame basis. Individual frame basis is not really a great idea, because then, if there are, I mean, like typically, right, you may find a continuity loss, right, because you are not really carrying information from the previous frame to the next frame and so on. And typically, people expect that, when you have a video, you use frames around, right, and not just kind of use a single frame as a standalone, right. Again, all these are different approaches. Some of these which we will kind of say touch upon, because it's huge. I mean, right, I mean, if you take one way, if you take video, then there will be, right, I mean, 15 methods out there. So the idea is not to go through every method. The idea is to convey as to what is out there, right. Then road extraction from satellite images, this could be another thing. So you see, I mean, say something is hand drawn, right, that's what I'm saying. That's like the ground truth, right, down below. So somebody has drawn so that's a lot of work. But yeah, I mean, right, it's possible these days, right, I mean, okay. And object tracking, right. Now, see, right, this is like one level above what we are saying, right. When we said detection, object detection, we are just putting a bounding box. Now, what is extra here? You are able to also tell which car continues to be in the video, right. For example, you're following 2, you're following 4, you're following 5, and so on. Now, this is actually a simpler case, but on the left is slightly more complex, right, because you are having people mingle, and then they go off. Then you have to still maintain a continuity. Now, this tracking, right, if you look at these kind of problems, they are still, I would say, somewhat simple, because the object is out there, right. I mean, there's a big what do you say? There is enough features to extract of the object. Okay, that is what makes this kind of object tracking easy. But then I can think of problems where you cannot do this. For example, right, even in our lab, right, we are working on a problem where it's like you're flying, right. I mean, it's like it's like this one, a defense scenario. So right, when a guy is flying his plane, right, I mean, so somebody is firing something at him, okay, there could be multiple things. Either somebody is firing a missile, or there could be another bunch of other enemy aircraft which are firing at you. And when this guy watches on his screen, right, all that he will see is dots. I mean, you don't see the whole big plane or fighter aircraft. You don't see all of them because they're all very far away. All that you see is a dot approaching, right? And then you'll see several dots. There's no feature like this. It's not like a big bounding box. You've got like 30 by 40 width. Nothing. It'll be like 3 cross 3 pixels. That's all you will have. And then there could be multiple people, and you have to kind of make out which one is coming at you, which one is an enemy, which one is not an enemy, and you have to track. Because only by tracking, right, you will know what this guy is up to, whether he's, because right, they will follow you, right. If he is an enemy, he wants to bomb you, right, so he will try to follow you, right. So there, things become very, very difficult. I mean, it's not like this, right. So again, that's what I'm saying, right. So I mean, how one kind of teaches this course, right, is entirely up to the instructor, right. I mean, what their own experiences in the area and so on. So each one of us will give our own flavor, right. So yeah, so I'm saying, right, that these are standard slides, but then you could have situations like that. Maybe right down the line someday, if we get some time, I'll show you things like that, right, which are much more difficult. And then post estimation. See, for example, even the earlier one, right, we are actually looking at working with the sports people. Okay, so in fact, right, we had actually been to the National Institute of Sports, right, which is Patiala, right? That's where it is. It's like an IIT for sports. Okay. And then when we went to the boxing arena, right, we actually went there, visited the place, and the boxing arena is like your international arena, right, how it is, and then they have a camera. The idea is that, right, if you wanted to do this kind of tracking, but then two people are boxing, right, and you want to track, that's very difficult because they keep on changing their position, right, it's very quick. So how do you know that, right, person one, you have to keep track, there is what is called occlusion. I mean, because one guy is hiding the other, you don't always get to, and you can't put like 10 cameras, right. So such challenges are also there, and there it's also a deformable object, right. I mean, again, right, there's a twist to the other ones are not deformable, right. I mean, these are all like rigid objects, right. A car moving, person is of course deformable, but at that level, right, you're not worried. But then, right, what we are looking at is the pose estimation, right, something like this, where you kind of compute joint angles, right. There is again a 2D pose versus a 3D pose. So the idea is that, right, you put a skeleton, right, on the body, and then the skeleton should dynamically vary, right, as a person moves. And you can do various things with this, and people do fun things like making the other person dance in a similar way and so on. So there's a paper, right, what is that paper? Anyone can dance, huh? Right? Yeah, something like that, right. Now, but the point is that we are not into dancing and stuff, right. So we are interested in, for example, if you had a boxer, right, so can you find out, right, what his angles are, I mean, whether the angles are correct, or it could be a javelin throw, right. So when the guy throws, right, I mean, is his angle correct? So all these, so again, right, the application area could vary, and then again, the kind of challenges that you then face, right, would also vary. Then you can have activity recognition. Ideally, activity is more like a video thing. I mean, here it's actually a still image is shown, but ideally it's a video, right? It's an activity of somebody jumping, somebody standing, and things like that. Yeah, I mean, it depends. So for example, if it's a boxing thing, it could be a left hook, right hook, I don't know, whatever they call that, right? Uppercut, so things like that, right? So you might want to identify what action happened when. So that's also to analyze the weaknesses and strengths of somebody, and then, right, you can kind of give that person a feedback, right, that, hey, look, right, this is what your opponent was actually strong at, this is where you missed out. So all that information, right now, right, there's a coach that does all of that, right? So the coach has to sit there, watch, then they record the video, then the coach goes back and keeps watching and then says, okay, what's going on. But can you give an immediate, and how many coaches do you have, right? So if you look at the number of people that might want to use this kind of method, right, you could just have it for free for everybody, right? Whoever does boxing, right? A kid in your street, right, is learning boxing inside some small little room. Give him, right? He'll get that information immediately. He can't afford a coach, right? So I think the right thinking is like that, right? Can you just make it open so that coach can come much later for very, very finer aspects, but for the initial, the learners, right, you don't need that probably. And then there is a captioning, right? I mean, all this is still like a semantic task, right. So captioning is also very high level, right. For example, you have to tell what is in the image, you have to capture what is in the image through sentences. This is again all done in a supervised manner. Okay, even today it is all very, very supervised in the sense that you give the caption, you keep on showing, and that's why these things can also go very badly wrong. I don't know whether you have a wrong example here. See that the yellow school bus parked in a parking lot, that is not a school bus, right. So that's because it's yellow, right? And it must have seen several images that are yellow, and that it must have recognized a school bus. So it just goes and thinks it's a school bus. That's where, right? That's where a human being is still, right? Thankfully, we are still way ahead. I mean, otherwise it will be trouble. So this geometry, right? Okay, so right, this is how the stereo is, right? So you have so you have, right, one camera, okay, that kind of looks at a scene. So here is your scene or object of interest. You're looking at it from here, then you go here, and then you again look at it from here. And then what you do is, right, so for example, if you kind of do a back projection, right, of this ray, okay, and then right, I mean, so ideally, right, your image plane is typically to the back, right, but it's okay to, right, put it in the front. We'll talk about it later. And then if you take this ray, right, you don't know where exactly is this object. Right? If I just have one camera, right, and if I go back, trace this ray back, I don't know where it ends. Okay, that is the reason why you need the second image, because then you take one more, and then if I know that this point, right, here we have taken one point x, whose image is here, and its image is x dash here. So this is a correspondence, right, that I need to know very accurately. If I know this correspondence, then I can draw, but then I can back project this ray, and wherever they intersect, right, ideally that is where the rays are emanating, right, of that object point. So that is why you need these two views, right, and then this again brings up its own interesting aspects. There are I mean, it's not that easy, because establishing point correspondences and all of that, right, is again a challenge in itself. We will talk about, what kind of features are typically used for such things, features that are robust, because you shouldn't get fooled, right, you shouldn't map a wrong correspondence. Suppose I said, actually, right, if it was this, and suppose I wrongly said it was this, then I'm wrong, right, then my depth map will go wrong, and therefore a lot of it depends upon how well you can do a correspondence matching. And you can also talk about depth from a single image, right. I mean, the earlier days, right, we used to talk about defocus and other things as a cue. Now they are even talking about deep learning methods where this is exactly like I said, right, where when you train, you have a monocular sequence, as it is called. You're just one camera and you're moving, and then, like I said, right, you can do depth maps in a self-supervised way if you don't have the ground truth, and then eventually after training, right, you just show one image, and then it is supposed to tell what is AC depth map, and yeah, right. That's what is shown here. We'll go through some of these things, okay, during the course. And this is the structure from motion that I talked about. So here, right, so you can actually view it from different angles. This is like a texture mapped onto the 3D point cloud, and right, and so here is where, right, you kind of, so it's like saying that your cameras are all around the object, right, here, you kept these cameras, and now, right, you are able to build a 3D model. This is still a very rich area, by the way, mathematically as well. I mean, okay. And then photometric stereo is again another kind of thing where you don't move the camera at all. And in all of this, right, if you notice one thing, the object is still. In many of these situations that I actually discussed, right, the object was still. Imagine what happens if you had a moving object, right? We seem to be solving this problem just like that, right? I don't have a problem. You move, I'll still tell where you are. But the moment you have a stereo algorithm, right, where you have something moving, right, it's not at all easy. For example, right, one of my students is doing ball tracking, right. So if you bowl a ball, and if I want to track the ball using a stereo pair, basically what was the cause of the problem, that we still couldn't get to the kind of accuracies that you typically find in stereo? It's simply because the cameras were not exactly in sync. There's a fraction of a second difference between the two, because they are not hardware wired, right. And what happens, so because of that, a moving guy, right, see, ideally, right, they both should see the same action at the same time, right. That's like, then it's like relatively still. The ball could be moving, but at that instant of time when I capture, they both see the same thing. Then it's okay, you can still solve. But what if this guy sees the ball a little away from this guy? Then what happens? The ball has already moved a little bit, right? And therefore, it's no longer that both are seeing the same point. See, when I say that this point projects here, this point projects here, the point has to be there. It can't relatively move, right? But if you have a delay, it's like this guy is gone a little bit, and that's enough to kind of, right, kill the whole thing. So right, that way, what we are still saying is still a simpler problem, right? And then you have the photometric stereo, where this is somewhat simpler in the sense that you don't move the camera, the object of course is not moving, but you change the light source. So if you see, right, only the illumination is changing, right? If I go from one image to another, there is no other change except that there is an illumination change, and this itself can also be used as a cue. Okay. So the point is, right, now these are still not so very easy, right? I mean, as I kind of, right, put forward, it may look like all this is doable, and therefore, right, it's great to do. But the thing is, right, you can also have various issues, right, that you might have to deal with. One of them is what is called a viewpoint variation. That means, right, see the same person, right, could be at say different angles, inverted, sideways, right, and and each time you have to recognize, right, that person as the same person. So what is called a viewpoint variation. Another challenge is what is called illumination, right. So it's the same scene, but then the illumination has changed, and you know what, all this is still a big struggle. For example, low light photography, right, is an emerging, I wouldn't say not emerging, it's already there out there, right. A lot of people are trying to solve problems for, let's say, low light, right. So for example, if you can do object finding in good light, can you do that in low light? And people are even thinking of merging audio with low light, right, because audio has a different information, right, and therefore can you fuse it with low light in order to be able to make inferences that can be as good as if you had good light. Then some people do it as an image translation problem, where you have a low light and then you want to generate a good lit picture of the same scene, right. So again, right, what viewpoint you take changes, but these are all challenges that one has to scale again, right. I mean, so why do you think this guy is so tall and the other guy is it like they are physically like that, or you think somebody is playing a trick here? What trick is being played? Anybody? It's not true that that guy is actually that tall and this guy is that short. See, the thing is, right, this guy is far away. This guy is actually very close to the camera. Okay, that's why it's looking like that guy is very short compared to. So again, right, so such tricks, but then right, this is a perspective, and again, right, I mean, you need to be able to deal with this. Then deformation, right, is what I said when I said that you can have deformable objects, right, where for example, a horse, right, doesn't come in the same pose every time, right, it has a different pose different times, and you still have to tell that, okay, it's a horse, right. So things like that. Occlusion is another, right, where, like I said, right, I mean, something could be actually hidden, right, I mean, it's not always true that you can see everything, right. See, for example, I can't see his legs because of the bench, right, that's occlusion. So if I had to build a 3D model for him, right, it won't be easy for me because I can't see certain portion of him. It's not. And then background clutter, like I said, that object tracking, like I said, right, in that, when you look at a missile being fired, if you look at the background clutter, right, that's what actually makes a problem tough. If it was just the point alone, you could easily track it, but then around it, right, there'll be so much heat and all that, and this point will be, and the only notion that you have is something is moving, and you have to really bank on that, right. So again, background clutter could just spoil things for you. It doesn't add any value, and it could simply, right, throw your algorithm off. Motion is again another thing, right. This is very interesting, right. I mean, when things move, right, you must have seen a blurring effect, right. I mean, there is a smear, and that smear can kind of right, completely take even the current deep learning methods and all, they are all trained on nice images, clean images, and all. The moment you show them something, that's a little off, right, blurring and all, right, they will struggle, right. We have already seen that, okay. Then intra-class variations, okay, and so on. So the course content, right, is this. So what? Yeah, maybe right. I'll kind of say, right, talk about this in this and next class, and yeah, just about 5 minutes, right, I will need, and then some reading material, okay, which anyway, it is all going to be there when I upload it today. And these, you don't have to buy any of these things, right? As long as you attend the class, that's enough. Don't have to buy any books or anything.